Hello everybody, welcome to another stream. How are we all doing? That's good. So last stream, we made some good progress. We got the binary tree working. So we want to build a quad tree. Not quad tree as in like the collision one, but just 4 nodes per child. Up to 4 nodes per child. But to do that, we have to build a binary tree first on the GPU. Hey Glorious sir, welcome. Welcome, good to see you. Oh my baby boy, go to sleep. Right. I've muted him, hopefully he goes to sleep. Anyway, yeah, so I want to quickly double check the code. Yeah, so we've implemented this CPU side, we've built this graph here, and it builds the graph correctly. It validates every node is connected to a parent and has been visited when we traverse down the tree and traverse every node. So all of this works perfectly fine. So we've built it on the CPU in a way where we can just copy it to a shader and it will just work the same way. So that's really nice. I want to quickly double check the code and see if I can remove any aspects of it while I've got it in this testing environment where we can validate if my changes break it. And then we're going to turn this binary tree into a quad tree. And if we have time, we'll start moving it to the GPU by writing a shader which removes any duplicate, doesn't remove duplicate Morton codes, it will make sure that they're unique. Because if you have 2 that are the same, it doesn't make the tree very well, unfortunately. But how are you doing, Glorious sir? Good to see you. What have you been up to? Yeah, so the code is implemented from this paper, which we've been over the past couple of streams. I've looked into this implementation a lot, which implements it. And there's also a blog post by NVIDIA where they talk about it as well. So there's 3 different resources that we've been using. So I just want to quickly look at the code a bit and see if we can change a few little things about it. So the thing I'm most interested in is this here. There's a guard. Like if you look at the paper, it doesn't have this guard in it. Or maybe it does. Let's read the paper. Here it is, enhance. So this is that function here. But yeah, before the first, there's a while loop here, and there's a thing called delta. There's a sign in L max multiplied by 2. Alright, so there's the multiply by 2 while doing this. So that's the common upper bits function, which is here. Well, it's also here inside the loop, right? So you're saying run that first. Can this just be a do while loop, or it's got to be a do while do loop or something like that, I think. But yeah, I think this is possibly a bit silly doing it this way. Maybe how I'm going to change it will just make the same code generation, but no, it wouldn't, because I'll remove that. Yeah, and then it'd be one of these. So basically, the way that I'm thinking about it is you put this in here, you invert it the other way around, and then you break. And then you move this thing up here and delete that, and then Bob's your uncle. I think because yeah, because this was already down here. It's duplicated. Yeah. So it's saying, yeah, set delta to -1. If you can index, update this delta thing, then, you know, if the delta is less than the min delta, then break. Then do that, multiply by 2, update the index to lookup next, and then, yeah. Yeah. Right. So we want to do the same thing again, but I think that's better because I'll result in less code, I think. Low energy days didn't do much. Trying to output some sound with Win32 CPP API from C. Nightmare. Pure nightmare. Sounds it. I've not done any sound programming. It's one of the things that I want to do. I'll probably do it part of this project. Have you done many sound projects or projects with sound programming, audio programming? Glorious. It's one of those things which seems like it could be a bit of fun. It's that and networking seem like some like things you do in the low level which seem a bit fun. Once you have your hardware abstraction, I think. Hey Dora, how's it going? Yeah, we're cooking. Yeah. Just things are progressing, which is great. What have you been up to, Dora? Didn't get a chance to ask previous stream. How's your busy days and your wife's quarantine? Yeah, my days are still super busy. I'm juggling a lot right now. I'm quite tired, but the wife's car has been passed. I had to polish off the lights, and I had to get the wheels replaced on the car. Well, the tires, the little wheels. Thankfully that passed, which was really good, which was really nice. But I've been super busy, quite tired. But you know, things are good. Things are good. Recently just had a every July we get the salary increases, and I was quite happy with mine this year. So that came last week, which is super nice. So yeah, happy about that from work, which is really cool. Also had a party at work, and my days. We had a party on a Tuesday, and then went to work on a Wednesday. Just did planning and stuff. But yeah, I had that type of foggy brain where I would try and recall something, and I'll just start talking, and then it's like, you know, you're just like frozen. You're like, I'm trying to get the thing I was just trying to remember. But yeah, it's good. Good. I had a good time. Got to see a bunch of people, have a catch up, which is super nice. Super happy about that. Yeah, I don't think we can change this code too much, to be honest. This is pretty tight. Right, so let's see if we broke anything by removing that extra if statement. And just cleaning up the logic. Right, that seems in a similar sort of place. Let's give it a bit of a drag. So we're generating this binary tree. Notice that it's not perfectly balanced, and I think this is what the paper does. Is it knows, is it splits, it puts stuff deeper where things are close. It goes deep where things are close together, I think, is the way of saying it. So things that have... Is that the right way of saying it? Because this could be perfectly flat. No. Yeah, where things are close together, they will be... Yeah, it might be that. Yeah, so if things are close together, they'll obviously be deeper and closer to each other. But it's not perfectly balanced tree, if you will. Because this could just be perfectly balanced along this row, I think. But some go a bit deeper. So it's pretty clever. So essentially the way you can think about it is every bit decides if the branch goes left or right. Left to be 0, right is 1. So you can think of this first bit meaning this top node. Oh, little man, why are you crying? Let me look at my boy, BRB. Right, so yeah. I looked on the monitor and I couldn't see him anymore in bed. And I opened up the door and he was just hanging off the end of the bed. Like, and just looking at the door waiting for me to come back. And he's just started crawling. That's insane. I need to move his bed down to like tomorrow. Like he's starting to be able to get near the end of the bed now. Crying out loud, this boy. Oh. I'm watching him now, he's crawling. I might put some white noise on in his room. Oh, for crying out loud, it's such a BRB. Right. Hey, welcome back. So I put white noise in the room. I'm hoping it's just going to get drowned out with the white noise and fall asleep. He used to do that a few months ago, but we've not been using it for a while. And this boy, he's just started crawling and is going and crawling in his bed. Anyway, back to the chat. Haven't worked with sound much. Did some basic sound output with direct sound and some simple mixing. Nice. Yeah, sounds cool. Much more than I've done. Yeah, it sounds awesome. Well, what are you planning to do with this new sound thing? Is anything much more advanced than that, or just doing the same thing? What distro am I using? I'm trying to use Linux after FreeBSD, and the file structure is less logical. I'm using Manjaro Linux. Oh, for crying out loud, it's got up again. I don't know why it's not calm. Damn it. Yeah, I'm just using Manjaro Linux. It's Arch-based distro. Right, we'll look at him. BLV. Alright, welcome back. Yeah, so what we're trying to do next is change this into a quad tree. So simply if we remove a node, right? If we remove these two nodes on this level, the two siblings, then 0 can point to these 4 nodes, and it's going to be that simple, I think. So I'm thinking about, so we could probably record a depth in the node itself, in that binary tree node, record a depth value. With that depth value, we can check if it's odd. If it's odd, it disappears, and it replace it, and the parent will, you go up to the parent and do increment a value, and you can use with atomics, you can know if you're the first one to increment the value, but if you're the last one to increment the value, then you can yeah, you can yeah, you'll be able to patch up all the children into the right place, I reckon, when you make the tree. Yeah, I think it's going to be quite easy on the GPU. So I'm going to do a different implementation CPU side, and then we'll just do a different one on GPU. But so, I'm actually thinking before we carry on with this, I want to probably change the seed. I want to change the seed because we've just been using the same random number generation for the Morton codes. So I just want to quickly double check to see we're not breaking anything. So this is a different configuration. Let's just test the nodes out. Right, it's not triggered any assertions. I'm just going to double check those assertions are in there as well, because I don't think we commented them out. Yeah, they're still here. So all nodes are getting visited for the ones that we're generating. So that's good. Let's do one more time, and then we'll make it a quad tree. Where's the seed at? Yeah, it's funny how bad the rand function is. Well, in C. Well, maybe it is kind of random. But yeah, you definitely get... Yeah, I guess most of the time you're on like pseudo-random, but it does feel really random sometimes. You get a lot of the same numbers. For now, I want to figure out more low-level API to introduce it into the platform layer, but eventually I want mixing to be more advanced, processing related, 3D environment, sound propagation. Amazing. Sounds cool. Have you seen the... No, I should be looking for... Have you seen... So this is, for those who don't know, if you're doing C programming and looking for a library, always start looking here. I don't know if he keeps this updated. He's 5 years old, but C is many more than 5 years old. There's tons of good libraries here. But yeah, if you're looking for libraries for things, start here. But there was one, it was a mini audio. Have you looked into mini audio? I've heard that one's quite decent. I'm not sure though, but it's like a, yeah, platform layer, I think, for audio. Yeah, I'm not sure what it's like, to be fair. Some stuff, it's probably, I probably want to look into these libraries and learn like APIs and then dig into APIs and see what's up, you know? But yeah, good times. Right, let's make that, let's make them four, let's make it a quad tree. So instead of a binary tree, quad tree. So on the CPU, I'm just using this data structure. Our GPU data structure is not going to look like this. This is just so we can debug it and do some nice visualizations and things. So we're just going to use the same one again. On the GPU, they're going to be different data structures because on the GPU, you're going to pack everything down. I'm going to sitting up again. That boy. But you're going to pack everything down into as few bytes as possible, basically. So it's going to be really different. You know what, I might put him back down and give him a toy again. Or give him a toy, maybe. Maybe get his teddy bear. Or something. Damn these things. Right. 2 seconds. Right, he has his teddy bear now, see how that goes. Strange boy. Right, so we encode the depth in here, I think. When we draw it... Yeah, you don't know the depth when you build it. So how are we going to know where to split it? It's not that simple. Let's take a look at the thing. So the only reason why we have the depth information is because we traverse the tree from top to bottom. I don't want to do that. So when we build each node, in the paper it does talk about how to deal with it, but effectively you want to You want to somehow know so if a thread just starts on 8, you can go to here and realize it's a leaf, so you can get rid of yourself, but that's not really a good metric because the rest of them can't do that without keep going, without looking at more nodes. You could remember the Morton code. And so there'll be a bit where it differs. You can remember the Morton code, and there'll be a bit where it differs. But that doesn't really help you find out where, if you can get rid of these. Or you could just start at all the leaf nodes and just traverse up the tree and... Yeah, I think that's the only algorithm we'll do on the GPU. Because we'll do it when you build the tree anyway. Yeah. So there's an algorithm where you start the leaf nodes of the binary tree. All of them go up to the parent and they mark the parent and say, hey, I've been here. And if you're the last sibling to be here, then you will build the bounding box for the parent node, right? And then you'll carry on. You'll go up and go up again if you're the last sibling. So it's a way to sort of cancel out threads and things. So we'll be doing this anyway when we build our bounding boxes for the nodes. So I'm thinking about combining the thing that builds the quad tree with the thing that computes the bounds for the tree. So in one step, that way it won't be a waste of touching different memory, I think. Yeah, I think that's the best approach. So we'll implement it so we can see the graph on... Yeah. So the issue is that... So we could traverse down to all of the... We can use a recursive function and then basically go bottom up just to see how that looks as a tree. And then we can... So we'll just call this one quadify. So here's your binary nodes. Then you have your quad nodes. We'll make a copy of it. Or should we make a copy of it, or should we just do it all in place? No, we'll do it all in place because that way I don't have to allocate any more things and we'll just comment it out. Right, so that's quite good. So the basic idea is we're gonna recurse down like the draw function does, and we're simply going to right, so after you call quadify, so you would have gone down, and now you can know if you are... So I think we can have a boolean that gets passed up, and you can know if you're... Yeah, but you can't do it in a simple odd even way. This is the problem with going down to the root, because you'll be like, this one will say, so these ones will be like, hi, I'm the leaves. So you can start splitting. MIDI audio uses the was API for Win32. Good reference, nice. Sweet. Awesome. Glad that helped. Yeah, I'm not sure what it's like on Linux, because I know there's a bunch of different things like GStreamer and that, but I think they're more higher level. So I think these leaf nodes be like, hey, I'm a leaf, you above me should join me your sibling. But this one's like, I'm a leaf, you above me should join. Yeah. So this one, yes, this one will go, I'm a leaf, join me your sibling. And then this one will say, I'm a leaf, join me your sibling. Then well, what should it do? Because in this case here, where this one's a leaf and these two are leaves, if these two were to join together, or you would delete this one, and then you would join. Yeah, sending that child cap because that's always two. So that would get rid of. You'll get rid of that one. And then these two will be linked under this parent. So you're saying. So these will say, don't get rid of me, don't get rid of me, don't get rid of me, get rid of me, right? So then this will have two that say. So because this one says get rid of me, because both my children say don't get rid of me, I'm going to say get rid of me. Then it goes to the parent. This says don't get rid of me, this says get rid of me. So I'm going to get rid of this one and put these two here, right? As a direct child under 7. So then 7's going to say, because this said don't get rid of me and that says get rid of me, I'm going to say don't get rid of me, right? Because, yeah, so this one says don't get rid of me. So this will have 3 children under it. This one will say, this one says don't get rid of me because I'm a leaf. So that says don't get rid of me because we, said that. So then this one's going to say, hey, get rid of me because both my children say don't get rid of me. Right, this could work. So that's going to join 3 there, but equally, you've just got, this could have been joined into a 4, and you've just split them up. But then maybe this is a good idea because of the way. So we could implement this quickly just to see how it looks. There is also the paper we can look into. But I think this is a good first start, and we can just see how things end up looking. So we were saying, so you get an A and a B. So if you have children, you'll get an A and a B. So you quantify, get rid 0, get rid 1. So say so what you're saying is if get rid of 0, we're going to, so we'll get the 2 results, and then we're going to put our children count back down as 0. Maybe. So if you get rid of, we want to kind of figure out how many children there are. Wait a minute. Why is it in a for loop? If you have no children, you say, don't get rid of me. Now these 2 things. You want to, if you're getting rid of one of the, if you're getting rid of one of the children, then it gets replaced with its, with the grandchildren. So if 0, so 0 could push this one out of the way. So it might be best to store the references locally and then just add them back on. So we're going to store them locally. So I think they're just pointers, right? Node 0. Well, they're node indices actually. So we'll do the indices. All right. So if you have, these two now. If you get rid of 0, then what you're saying is we're going to get this pointer. Node C for child. Then we're going to say, right, this is always going to have 2 children. So we're just going to put them on. So node children indices and children count equals child 0. Right. That's good. Then we want to do the same thing again. But for the this time we get node 1. Boom. So you only return true to get rid of me if both of the children were removed. So let's see how good this actually is. It might not be a good algorithm, but at least we've tried to think about something and understand the problem. So basically where we do the node draw, we can now have a different mode. So right, children cap. So let's move this here. So we'll have an if 0, children cap 2, just as a draw and done. But else is gonna do children cap. It's gonna quadify it, so it turns it into a quad tree, and then it draws the quad tree and then does a validation. So the problem is with the validation is what? The validation is going to look at all the leaf nodes. No, we just want to, it looks at all the nodes actually, make sure they all get traversed. This is no longer the case. We just want to look at all the leaf nodes. That's the new thing we're going to do. So let's try this out. Fingers crossed. Alright, we want to set. We didn't visit all the nodes, apparently. So we're going to comment out this assert and just see what weird thing we've made. Right. Clearly not helpful. I wonder why that is. The number of leaves have changed. Let's think about it. Or maybe we could treat it as a yeah, I'll think about that after. So what's going on here? What did we do wrong? So we fish those out. Mutate. That looks alright to me. All the children should still be reachable. So I'm going to put a breakpoint here, just so we can see how the draw function works. See why it's not going down. So we go into here, we'll see what happens. So apparently it has no children. Really? Interesting. So that's the next thing we'll look at. Why does it have no children? What did I do? So the most root node, well, we can look at that, isn't it? We can just follow it through. So the most root node, quantify, does their thing, get rid of me, no, get rid of me, no. Oh, of course, I set children, right. Only if one of them needs to get rid of. Wait, no, that's fine, that's fine. If you don't get rid of it, I forgot to write this part of the if statement, you need to add itself back on. Yeah. Whoops. Alright, so let's run that. I've got to remember I disabled the assertions. So hopefully that still works. The trap. Didn't delete the breakpoint. Alright, apparently we're good. I don't see a quadri though. Apparently all the children are being reached. So is it not rendering? Is something painfully wrong with this? I'm only seeing 2 children. That can't be right. Something is painfully wrong. That's okay, we'll find out why. Right, it's got room for 4 indices. That's good. Right. I'm going to assert that children is equal to 2. I'm going to assume that. So this is the assumption I made. And I want to know if that's valid. Right, apparently that's valid. Interesting. So why... Okay, so that's cool. Why does it only have... There must be one with... So let's see how many children there are in a node by the end of it. Bunch of 2s everywhere, apparently. What am I doing that's painfully wrong? So I guess this doesn't... ever happen. There'll be 3 there. So maybe this hasn't done anything. Strange. I thought that would have done something, but it's not. Let's re-enable the old code and retrace my steps. So I was thinking, these 2 say, don't get rid of me. Oh yeah, it's only if both the children say, don't get rid of me. That's the logic. If they both say, don't get rid of me, then get rid of me. That's it. Right, that's made it a little bit more split into 4s. It's interesting. it works. Like you're not always gonna get 4 at the top. I think if you're doing it from the bottom up, bottom down, you'll get. But you're getting some 3s here, another 3 there, 4, another 3 there. That's quite decent. So let's slowly move it up. So you've got a 3, a 2, and a 1. This can't be much better than that, really. The number of leaf nodes. That just goes there, makes a 4, right? Then it splits as a 3, then another 3 here, then a 1. Obviously different enough. That's not bad. 3, 3, 3, right? 3, 3. Okay, split it across there. That's interesting. See, this one, it seems to have a pattern where it expands over this way, and then when it gets a chance, it breaks down even more here. That's the sort of look I'm getting. No? Okay, yeah, I was wrong. It does change a bit differently. But right, there's a lot of 3s though, and 4s. Well, there's some 4s though, should I say. There's a 4 there, 3, 3. Yeah, it's a little bit concerning there's a couple of 2s there though. You would want it to split more at the top, maybe. Right, so should we look at think of another way to do it? I think this isn't bad. So let's go back to the 2. So there's that approach that we thought about. There's an approach where... So this is because we start from the roots, and we're trying to say when 2 of the children say, don't get rid of me, the parents can say, yeah, get rid of me, and then it will join up with its sibling. And the sibling might say, yeah, if the children join up with the sibling, and if the sibling gets rid of, the same thing will happen, you get a 4. In this case, you just get a 3. Right, this one of these 2. So that's kind of cool, but it's bottom up. So it's definitely weighted towards something. Maybe that's what you want to do though, I don't know. Right, but also another way you could do it from the bottom, because then this means we can do it all when we build the tree on the GPU in a multi-threaded way, which would be pretty sweet. So you could say they always try to join until there's too many. So it's just, so you'll be like, I have 2 children. No, sorry. You start on these guys and you say, oh, we only have 1 node each. Then this one gets here. Because the number is only 2, it can't do anything about it. Then this one points back up. Well, okay, these 2 probably say, we've got 0 children. Goes to here. And this one says, I got 2 children. No. But this one's going to say, we've got 1 node each. I got 1 node, I got 1 node. This one goes up to here and says, does it say I got 3, or does it just relay the information how it's got? So, you want this one to go and this one to create 3, basically, isn't it? I wonder if it will be the same. It will generate the same graph or not that we've just made. Interesting. So if these report, because you can't have this one report 3 nodes, because effectively it's not going to have 3 nodes when this goes, is it? So this one can report up and say, I got 2 children underneath me. And this one reports and says I got no children. So because so a bit of maths you can work out. I can have 3 children here because of that. This one will report back saying I've got 3 children after it's collapsed that up to here. And then this one will say none. So because this one will say I got none, it can work out, hey, we can get rid of a node and then have 4 children here. And that seems a lot better than the method we had before, because you can actually get these to all collapse up into 1, 4, right? So maybe that's the approach that we take. I just got to figure out the maths a bit for it. So we'll do another quantify. So go to quantify 1. And we'll call this quantify 2. Clearly the best names. So in quantify 2, I want to do that approach where you're passing up maybe the number of children. I'm still not sure about it, but it seems like it could work in some way. So quantify 2. Now, because you're doing so, oh, for crying out loud. There we go. So you're saying like children count 0, children count 1. So with this, then do Boolean. You won't get an error check there, and you'll be like, why is my thing only 0 or 1? Yeah, so U32, number of children. So the thing is, you will either have, so 0 children means you'll still get 1 node as a child if you keep. So 0 means you can't get rid of that child, your direct child. But you got to keep the node around, so you're always going to have 1. No, you always have 1 node. If you have a number between 1, you can't have 1 child. 1 child doesn't make sense in a binary tree. You will either have a 0 or a 2, or a 3 or a 4. So why am I making it that way? That just seems a little bit weird, right? Let's think about it in another way. Why don't I just return 1, 2, 3, or 4? Let's have a think about that. So these will return, imagine these return 1 each instead of 0. And so this parent node will look at it and be like, well, they both report 1 back. If you add them up and you get 2. Yeah, well, there's nothing I can do with that. Then you pass up and you go, hey, I got 2 children. Then this one passes up saying, wait, what does this pass up? Yeah, it passes up 2 because I got 2 children. This passes up 1 because it's got a node by itself. So then you do 2 plus 1 gets you 3, and you go, I can do something about that. So then it will go and get rid of the one with 2 or 3. Yeah, that's the logic. So we're actually going to return values 1, 2, or 3, or 4. So if there's no children, you return 1. You never return 0. So this would then be So you add the two together. So they're not children, they're grandchildren. So then you know how many grandchildren do you have overall. And so if you have 2 or less grandchildren, nothing you can do about it. If grandchildren count is less than or equal to 2, nothing I can do about it. Wait, it's always just going to be 2, but it's always going to return 2 at minimum at this point, because yeah, you can never return a 0, and the least you get is a 1 back. But yeah, we'll do that just in case. So you'll hear return just the number of children that you have, right? Which is 2 at this point, right? But you'll just return 2. Yeah, because there's nothing you can do about it. Now the next thing is like, well, I can do something about this. So what I'm gonna do is reset my children count. I'm going to... So at this point, it's going to be a binary tree. So you'll get your 2 children node indices out, and then you're going to go how on it. So you get rid of this child if this one... Wait a minute. You also... or if your grandchildren count... Say if there's 2 4 nodes. If both of your binary node children, right? So you're both your 2 children have, you know, children that add up to 4 or more, then there's nothing you can do about it either. So that has a number between... It has to be 3 or 4. Wait a minute. If there's 2... Yeah, then it's returned a couple of 1s. Let me have a look at that again. This returns 2 1s. This will return a 2. Yeah, nothing returns a 0, so you'll get a 3 in this thing. Yeah. So return a 3 or 4. If you return 4, you leave it alone because the next time it goes up, it will join. Yeah, I think that's right. That's cool, that's fine. Right, it's going well. So here, we want to get rid of this one if it's greater than 1. Yes. So if this child has a... We get... And then we join all of the So we're actually going to have to put for loop in here. We're going over to children count worth. Right. But if not, we just stick the child node back on there. Right, and then we do the same thing again. This time with your second child, and voila. So let's try this one out. This seems like it could be amazing. And if you reach here, you're returning the total number of children. There you have. This is going to be great. Yeah. Hopefully it's going to be great. Let's find out. So let's use the second method. Oh, I put -1. Good catch. Right, this one has changed. No, that's still the binary tree. Right, quad tree, here we go. Right, still runs. Something is painfully wrong. No, I'm not seeing them group up into 4s. Or maybe I am. But yeah, something's painfully wrong. They're not grouping up into 4s properly. I've got some of the logic wrong. What have I done? So I get the 2. No. Right, so if you have no children, your relief node, report 1. If the total number of grandchildren are either 2, 1, 2. Wait, that says. Yeah, you're only greater than 4. That's a problem. Right, that's better. Excellent. Right, so this one should do a better job of making 4s. But I can't verify that. I cannot verify that. So it can't do anything with these because it's just there's a couple of 4s here. So yeah, you're going to get a lot of nested. The deeper you go down, the more 4s you're going to get. Because it does a real good job of joining stuff. Like as soon as it can join stuff, it's going to join it. As you can tell here, it's quite. There's not many checks on the first node, but as you go deeper, the checks get more. Maybe this is a good thing, because if you're just to think about splitting up a scene, you've joined them closer to where. Well, it depends, right? Yeah, it really depends on the data, I think. But maybe when you traverse down the tree, like. Right, so I think that's kind of good. But let me go back to drawing the binary tree again and just think about it from if we're traversing it down with a ray tracer. when we're using a ray trace and we're going down the scene, if we say got rid of these two nodes here and made these 4, right, we did it from the top end of the tree, made these 4 direct children of this. I don't really... I'm not really sure. Because you could argue it as, you know, you check this one and it hits, so I want to look at these. But if I check this one and I miss, I don't have to check these. Then the other perspective is that the way I want to design the nodes is that 4 children nodes fit in a cache line. So really, if you was to get rid of these 2, you would just check these 4 and they'll be in cache, so hopefully you'll get less. You know, you'd do more checks, but I think it would be... Yeah, I'm not quite sure. But they're more of the granular checks. And if you're going to hit both of these boxes anyway, you're going to end up doing, you know, 1, 2, 3, 4, 5, 6 checks. So yeah. Maybe you want it to be more grouped at the top, and then the more you go down. No, I'm not sure which way round you want it actually. Maybe the way we got it is fine. Yeah, I think we can play about with it in the future a bit more. But yeah, it's always open for playing around with, I think. Right, so I'm happy with that. So what I would like to do is start moving this to the GPU. So let's write some shader code. The issue with the shader code is currently these Morton codes have to be distinct, unique. So we need to write a shader which actually just uniqueifies an array of integers. So we're going to make a new shader like every good graphics programmer does. You have a problem, you make a shader. You always need more compute shaders. So what we're going to do is find... Yeah, so I've cleaned up this code base now, so it's all in a good place. So here's all our push constants. We'll make a new... so this BVH construct, I probably want to make a BVH section because there's going to be a few operations when it comes to a BVH. Yeah, it's kind of interesting because yeah, we'll put it up here because what's interesting is we're gonna have quite a few little shaders, I think. It'll be fun. So I've made this BVH construct. We'll look at that one later because we've gone and changed our minds a bit. So yeah, we're still keeping the design, but how we get to that design is just a little bit more work. But we've got it all written out, so it's good. So the first thing I want to do is BVH Morton code. Well, okay, what I probably want to call this, I could just call it the uniqueifier. But I don't. So we've got the word distinct, right? That's another way of saying it. Nah, distinct, right? Probably not the right word to say. Uniqueify. Let's call it uniqueify. So we're trying to uniqueify U32. So basically you give it a bunch of integers, and the whole job of this one is to make sure they're unique. So we'll just increment them until they're unique. The grand uniqueifier. Let's do it. It is the grand uniqueifier. It's going to be amazing. We've got to think of an algorithm though. I've been thinking about this, and it's kind of interesting because there's different ways you can do it. And I'm trying to do it on the GPU. So I kind of want to make it as multi-threaded as possible. So yeah. Datas. What is it? Could just call it data. 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 The grand uniqueifier. Oh yeah. It's gonna be legit. We should probably put this in its own section, to be honest. Have I done that? Oh. Right, let's get a section header. And I'll just drop that here. Wait a minute. Oh yeah, that's the PBR stuff. I thought I put PBR in a separate section, not gonna lie. Oh, I haven't I? That's lies. I think I put some of it in there, but anyway, this is BVH. So BVH stuff. Uniqueifier. Uniqueify U32. Right. So, the plan. So you need to know how many elements you're gonna have, right? So my basic plan, let's get the whiteboard, is maybe I don't need the whiteboard. So you have an array of integers. They'll be sorted in order. Right, maybe I shouldn't call it. Maybe I should call it like Morton code uniqueifier, so it's more specialized because it has to be sorted. But what happens if you have 1, 2, 3, 1, 2, 3? So they're all in the same location. Then this one is 1, 2, 4, right? And then you have like 126, 127, you know, and then maybe, I don't know, 150. But so we can't have duplicates, but what we're supposed to, so these numbers represent a 3D coordinate. You know, we've used Morton code. If you don't know what Morton code is or the Morton Z curve is, look it up and you know what I mean. We essentially convert a 3D coordinate into a 1D coordinate by shifting the bits over and stuff like that. It's quite interesting. It's pretty cool. It makes a Z curve, as they call it, but puts stuff into a Z pattern, when you increment an index, it makes Z patterns. It's quite cool. So they're all, when they're near in this array because they're sorted, they're near in 3D space. So one method we want to keep everything here because every one of these represents an ellipsoid that we want to ray trace against. So I need to be able to so we also want to preserve order. These are all in the same location. These are in the exact same location. These are that's in the location next door. This one is probably also next door because of a Z curve, or it could have jumped a little bit further away. And so when it comes to dealing with these, we could take the approach where you spawn a thread and everything looks to the left or looks to the right. What am I thinking about? Yeah, because the problem is you've got multiple threads and I want to have them. Yeah, so I think let's just try and produce the result that I want. So we don't want to keep it in the same order. So maybe what we do is we increment, let's make the other array. So I'm thinking maybe we end up incrementing this by 1, this by 2. This ends up having to be incremented to this one. That's end up going up. And then that one has to go up. And so they're all going to get moved a little bit on the Z curve. So I think there's actually an image for the Z curve. I could have showed this. So we would have pushed, as you see here when we incremented these guys, these weren't even duplicates at the time. But because there's been duplicates before, they've pushed these up. And so these could have been sitting here, right? But we've moved them to there. Or maybe they could have been sitting here, but we've actually moved them to here because the way the Z curve works, right? And because the Z gets more macro as things go on, a jump from there goes over there, and then a jump from eventually up there goes all the way down here. So when you make another one of these, this bigger Z here up here, it restarts down here again. So you can push stuff over a big jump because you've done that. But you have to fill in the space. There's another way of doing it. Or the other way of doing it is taking the ones which are duplicates, picking them up and moving them. But then because you've picked them up and moved them, you've then got to move another array's worth of data as well. So you can't move it in place. You have to literally take 2 arrays and move the data from 2 different memory locations. So instead of writing to 1 array, you're then reading from 2 different arrays and writing to 2 different arrays. So there's a bit of a cost there as well. But if the overall BVH is better because of it, maybe that's okay. So with that approach where you're moving the numbers, you are physically moving. So it's like, say if you had 2 triangles that were in this same tile, you're picking them up and you're moving them quite possibly over. So they're the ones that get moved. But then you've moved them. Sorry, when I say move, you're moving where they're going to get arranged in the tree based on their position. So let me draw this out. Say if here's that. Your triangles are in here. Three triangles with the same Morton code index because it's low resolution. There's another Morton code index up here with a triangle. But then, yeah, so you're moving this one to go into this bin. This one's going to that bin. So then, even though it's like not positionally moving there in 3D space, it's going in that bin. So when you build that tree around this, around these are going to get binned with stuff. These triangles here are going to get binned with objects that are actually further away than this thing is. So outside of these, there'll be in some other Morton thing. Maybe they get binned with guys over there or something like that. If we did it that way. But if we do it the way where we said here, where we just increment all of them, what you're saying is this will get binned here, this will get binned there, and that will get binned there. Meaning that hopefully these ones that are really close to each other that happen to be in the same given the same Morton code index will be placed in a closer proximity to each other, so they get built into the tree a bit nicer. So the ray tracing shouldn't be so bad against it. But yeah, we should try and minimize that as much as possible though. We shouldn't have stuff literally in the same area. And maybe when we build the models, we can make the trade-off between, you know, the resolution, the Morton code resolution will be the whole local space of the object. So the smaller the object you build, the less of these collisions you'll get and the less of a problem this will be. So I think this is the approach, but we've got to somehow do this in a multi-threaded way, right? We want to increment the numbers until their siblings are no longer wait, what's the way of saying it? You want to increment the numbers until your left sibling is no longer greater than you or equal to you. Yes. So but that just sounds dependent on the node to your left, which is very painful for a GPU because if you've got a bigger array, you're just going to be starting you spawn a thread for each of these guys, right, which isn't a problem for a GPU because it has all of that in a register, right? 32 things in a register. But imagine if you have like thousands of elements. Well, many SIMD units is going to be sat there waiting for the one before. So I think this goes back to my wave prefix sum thing that I did, where we can do it in like groups or something. And then we just come back to them and increment them again afterwards. We could also decrement. That's another approach. Decrement and increment. It's an interesting one. So that means you could technically start from the left and the right hand side and then do progressively move in. But then that's only 2 threads at a time. So it's not really, and it's just So it's an improvement, twice the improvement, but it's not really leveraging all the threads again. So the other approach could be, right, I spawn all my threads down, and then I go, crap. This guy is a duplicate with this. You say, what you want to say is like, so I've spawned it here. Okay, let's just start simple here. I've spawned it here. So I'm going to look to my left. Crap is a duplicate. Look to my right. Oh, it's not a duplicate. That's fine. Right, hold that thought. We'll come back to this one. You'll spawn here. You check to your left. Am I a duplicate? No. Look to my right. Yeah, look to my left. Am I a duplicate? No. I'll terminate. You'll spawn a thread here. Look to my left. Am I a duplicate? Yes. So I'm going to increment myself. And then I'm going to go to the next one. Is it the same number as me? Or is the number I just left, so that I incremented it to 24. Is this greater than or equal to? Yes. Increment. Go. And that'll be fine, right? But then that's still not independent, because if a thread spawned here at the exact same time, it would have looked to its left here. So it's as if what you'd want to do is probably have the ones that have not got a duplicate to the left, but have a duplicate to the right. And these are the ones which are going to progressively scan ahead. But you'll still catch up if there's a gap, I think. Because what you ideally want to do is spawn a bunch of threads where they find duplicates that are spaced apart, and then it will just increment until it's solved the problem. But I think we're going to bump into other threads, so we can try out the algorithm again. So here we spawn a thread here. We check to the left, it's not a duplicate. But meanwhile, another thread could be right into that. I've got to have a think about that. Or another way we can solve this problem, if we don't want to do it in place, is we just copy one array to another array, and we don't do it in place, and therefore that will avoid race conditions. So that's something we can think about if we can't solve the race condition problem. But yeah, so we look to the left, it's got a, it's not a duplicate. Look to the right, it's a duplicate. So I will increment the right, and then go to the right again. Yeah, I think this is the way we've got to go, but we've got to do it in a way where we... Right, so let's put this one down here. This is the result. Let's reset this one. So I think what we want to do is make it such that this is read only. You know, we're going to fill the array from scratch. So this one comes in, it's the first one, so it can't look to the left. So it's just going to copy and put the value in there. Ding! But yeah, you can imagine this happening simultaneously at the same time. We've got to try and not create overlaps here. This one, and we'll come to the duplicates in a sec. So this one, again, we'll look to the left and the right. It's not duplicate, so these will all go in. Now we'll wait here. Actually, yeah, we'll just do it all in order. So this one will look to the left and the right, realize that it is a duplicate to the right but not the left. So this one is allowed to now just go off and take control. So this one's going to increment, so place that in there. So it's the thread that spawned here is the one that's taking control. We'll get to this one in a bit. This one's going to increment it then it's going to realize that this number here is less than or equal to this. So it's going to, put it to the one up from that. Then this one, yeah, but we're still going because we realize that this number is less than or equal to, because it's the sorting order thing. Then we put the next one in up from that. Then we realize this one is, less than or equal to, so we put the next one in, and then put the next one in, and then we stop there. So that was all from one thread getting there and being like, my left was not a duplicate, but my right is a duplicate, so I'm the one who can take control and do all of this. So this, now we've got to prove that these ones won't do it at the same time and mutate the new array. So this one is going to look to the left, realize that's a duplicate, so it's just not going to bother doing anything. Because the ones to the left would have started the chain of things. Goes to the other thread is also spawned at the same time as all of these guys probably, and it looks to the left and realizes, oh, it's the same, I won't do anything. Goes to the next one. Oh, not goes to the next one. Again, this one is spawned at the same time as all the other threads here. Looks to the left. So maybe we'll have to do some... See, I feel like you'll have to do some serious counting on all threads. They'll have to just keep poking to the left. Because you notice there's a gap here by 1. Right? And this one can't write here if this thread just went and made all of this. Right? At the same time, we'd be trying to write its value to here. But what we could do is, because what we could actually do instead is we could go, it looks to the left, realizes that they're not the same, looks to the right, realizes they're not the same, so it goes, okay, I'm going to try and put my value here. So maybe we'll have an uninitialized value of U32 max. And we'll realize, hang on a minute, someone wrote something here and it's greater than me, so I'm not going to put my thing in here. So you can do an atomic max. Wait, yeah, we can do the right that goes into here is always an atomic max, and that means that it will just not write this one. Right, so that's the way we can get around it without having to do an insane number of checks and have them always write out. Okay, I think this is possible. Yeah, so then this one tries to do the same thing, right? Looks to the left, looks to the right, not duplicates. So I'm going to try and put my value here with an atomic max. I forgot to increment that. Yeah, I think this works. This is actually really easy to do. So I think we've figured it out. So I actually want to rename it. Morton code uniquify. So we'll have a read-only elements, read-write elements, right? So DST, source DST. So remember, they must be sorted, and right, and there must be wand. Must be mem set. Right, so they're wand. All the bits are wand. Wait. All zeroed. So if they're all zeroed, yeah, no, must be zeroed, because then you just do the atomic max. Oh yeah. I think this is going to be good. So the code is actually very simple. We get our sv dispatch index.x. This is our source index. And we try look to the left, look to the right. And we want to know, we want to have is left the same? Is left not equal? So you're just going to say source index equal to 0, or so it's equal to 0, we'll say left is not equal. Yeah, and then, or if source elements, we can call these Morton codes. That can work. Morton codes. So we're putting the source index there. Take away 1. And we're going to then say if that is, so we need to fetch out our current Morton code. And if this is equal, is not equal, now you want to say if the right is equal. So you do a similar sort of thing, where if the source index is less than the number of Morton codes, yep, and this time, because if it's at the end of the array, it doesn't need to go and increment everything to the right, does it? So then you say equal and then plus 1. So with this, we should be able to, and I wanted to rename this to Morton code uniquify. So this will then be, so I'm going to say if these are both true, we're going to go ahead and is right. So if left is not equal and right is equal, we're going to go ahead and traverse until we're going to so no matter what, you always try and put your value down. You always try and put your value down there with an atomic max, always. So you always say BC destination Morton codes, and we'll do a lovely atomic max E32. I guess just call it index, right? Equals whatever your Morton code is. So you always try and do that. Now from here is when you'll try and increment the ones after you. So you always go do a little while loop. You say while maybe it's a do while, I don't know. While index is less than, maybe it's just a for loop. Right, so you increment the index like that. Maybe it's do while. Watch this. Every time I do do while, it will get rewritten. I'm hoping to be proven wrong. It always happens. So I think we're going to be fine here because it only goes to the right, because we've already done the check, is here. So we increment the index. Now we operate on it. Wait a minute. Yeah, that's the check. Whoops. Oh, I forgot to do another check actually. This needs to be, because of compute shaders, how they do 32 at a time, you need to do a balance check. Right, cool, that's cool. So yeah, you add the 1, and then you now, so you've got your molten code, and so you've looked to the one to the right. So we're imagining this one, looked to the left, realized it was less than, but the right is a duplicate. Oh, sorry, realized the left was not equal, so the right is equal, so it's gonna put the value in there. That's what that one is with the atomic max. And then it's gonna go to the right, and it's gonna be like, oh, your value is less than or equal to my value. So I'm gonna help. It goes to the right, your value is less than or equal to my value, so I'm gonna help you out. So we'll read out the next molten code, and it's gonna be like, oh, so if the molten code is, if this molten code is less than the next molten code, then we're finished here, right? We've reached the point where we've resolved all the duplicates. But here, we haven't. So what we actually need to do is compute. So you take this molten code. Wait, do you want to increment it by 1 here? You want to increment this molten code by 1 because this would be 1, 2, 3. When it goes here, it'd be 1, 2, 4. And you realize that, hang on a minute, this is 1, 2, 3. So I need to, store my 1, 2, 4 in there. So it does it again. Stores in the destination points the new molten code. Checks to see if, yeah, what is this do while loop even doing? It's as if you want the index to be incremented before then you do the check. I'm just going to move it. It's slightly less efficient, I guess. No. Yeah, I hate do while loops. Always end up refactoring it. Okay, I think that's it. So I think this is basically the uniqueifier thing. We're just going to double check it. So if we're the thread which is in control of enumerating the values because the left is not equal and the right is equal, we're going to go ahead and take the Morton. We're going to increment the value by 1. Sorry, increment our index by 1, increment the Morton code by 1. Gets here, our Morton code is 124. We pick it up and we go, oh, this next one's 123. So we're going to then be like, is 124 less than 123? No. So we carry on. Put 124 in there with an atomic max. And then go back around again. Go to the next one, make it 125. Go to here, do the same thing, put 125 in there. So if a thread writes to the same location, it's fine because we've got the atomic max. And because they're sorted, we're trying to write the maximum value in, and that's okay. Now this is great. I like this one. So let's comment it so it's all good. So we check, because I want to be able to come back to this, or other people to read it or whatever, right? So we want to say copy over the value. Wait, could you do it all in place? You would need atomics. And you'll probably get race conditions. So if you look to your left, yeah, yeah. No, we're keeping it this way. So the issue is it's got to have 2 arrays. But that's okay for the build process, maybe when you're trying to build a BVH. You can have a bit of scratch memory maybe, I don't know. It'd be good if you didn't have to do it, but then you'll be using atomics everywhere and that would just be messy. This is only using it in one array instead of... maybe. Let's see if I can convince myself if it's possible. So you'll be like looking to the left. And that could be greater than or equal or less than or whatever it is. And it could trigger you to start going. Yeah, I'm not going to bother doing anything more crazy than this. It could be done in place. But we might need another buffer anyway to keep track of stuff. I don't know. I'm quite happy with this approach. We can always improve it later, I think, if need be. Or if it seems annoying. Right, so we copy over the current Morton code to the destination array. We do not need to worry about race conditions here, since we atomic max. Since we atomic max a sorted array, so if a previous thread came here before or comes after, I need a way. Man, I need a good way of describing it. Rather than just saying, "Hey, the correct value would be in here," I need to describe what is the correct value. Copy over if there hasn't already been a higher value written there. Copy over the Morton code to the destination array if there already hasn't been a higher value written there from a from a thread that started to the left of us. To the left of us, but if a thread that started to the left of us hasn't marched to our position, dealing with duplicates. That's probably a better way of saying it. Copy over the current Morton code to the destination array if there hasn't already been a higher value written there from a thread that started to the left of us that hasn't marched to our position while not dealing with duplicates, while removing duplicates, something like that, right? So we're not going to bother carrying on here. We terminate. Yep. So I don't like branches like this because it means that I cannot put a nice comment. So this comment is saying, like, you know, exit here as if the left value I shouldn't invert it fully like that, I should do it like this instead. Oh, exit poll. Oh yeah, I've already been down there. Me and my wife went down, did our votes. Have you been and done your vote, Swankfuck? Oh, you mean the exit? Oh, I see, exit poll. Exit here if the left value, if we are not the thread which starts dealing with removing duplicates. A thread starts removing duplicates when its left is not equal and its right is equal. Right, now here we're going to say march to the right. march to the right. And incrementing the Morton code. The Morton code. And writing the value as we go. We stop when the Morton code is less than the when our Morton code is less than the one we read, the one we have marched to. AKA resolved all the duplicates. Resolved all the... AKA when it has resolved all of the duplicates. Yeah, so this will mean... So the thing that's good about this algorithm is that a thread is very short-lived. It just checks the left, checks the right. And if it doesn't march, it just tries to write a value, done. If it marches, it just marches so long as the duplicates are there, and then it exits, right? So there's, and the best thing about this is it does it in a, you could have multiple threads doing the marching all at once. Yeah, it's pretty decent. What about... Let me think of an edge case. I think I've thought of an edge case. So let's change it a bit. Let's change it such that there's a duplicate here. And there's a duplicate there. Bum, 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 bum. I live in Italy, but asked my mum to be my proxy vote. I'm British in Italy. Oh, fair play. Nice. Yeah. It's pretty crap situation here, to be fair. People bailing on the Conservatives, and you're left with Labour, which are questionable. And then you can't vote for... Well, you can vote for them. You know, but people don't choose to vote for the smaller parties because of the game. And the game is you only vote for the big parties because if not, it's a wasted vote. So, you know, great. So yeah, two poor choices. Let's go. But yeah, here we go. Politics 2024. You just voted Lib Dem, at least I won't feel guilty of Labour or crap. Yeah, see, if you don't... Yeah. I think people should vote for the parties they want to vote for and not play the game. Because playing the game is just... It's not getting us anywhere. But then, yeah. I think when it was Brexit, my family voted for Lib Dem. Yeah. Because they wanted to stop Brexit. Yeah. But we've done Brexit now, so that's over. It wasn't a good short-term choice, put it that way. It could be a good long-term choice if we have a plan, but we didn't have a plan. So yeah, now we're just dealing with that crap. Um, yeah, so we want to see if this is an edge case, that because theoretically this, when you spawn a thread here and here, they're both going to look to the left. They're not equal. And then they're going to look to their rights. So this one is going to look to the right. Oh, it's equal. This one look to the right. Oh, it's equal. So these two are both going to start marching. So the question is, are they going to be a problem? I don't think they are, because we're using the atomic max. So they're both going to start marching and run to the same place, but it's okay. So this is going to go here, 24. Then it's going to go here. But meanwhile, this one's gone here, gone there, 25. But then this one could also at the same time look there, do an atomic max, write 25. Look there, realize it's greater than, less than or equal to, whatever it is, right? Then atomic max with 26. Yeah, that works fine. No problems. Legit. So, yeah, let's wire this boy in and let's see if it destroys my GPU or not. And this will be the first shader of the BVH construction that we will fire off. Man, that's good. I'm happy we came up with that. I've done that twice today, just make up two new algorithms. It's pretty sweet. If a program had good security, would you register to vote using your social security number? I don't know how the UK works. Then voting would be real time. You can see average. Change your vote at any time. See, the problem with changing your vote is that changing your vote in real time and seeing it live, that adds a complete new element to it, where it's because I think it would be complete chaos right up until the last minute, because people will be changing their mind and seeing how it is and reacting. So no, I don't think it'll really settle. So yeah, it would settle earlier, but it won't really settle late. I think it will be quite chaotic late in the voting. So I think the live aspect will have to go. You just put it in and you've done it. When it comes to voting online, security wise, there's no secure system. So I don't think that's reality, unfortunately. And also you got the problem of, you can have a secure system, but what you don't have is a secure, you don't know that a user is voting for themselves. So I think it's law in the UK where you can vote for 4 people. You can give your friend your card or whatever, and they can vote for you. You can do 4. I don't know if I agree with that system, but I guess if you have someone that's ill, you should be able to go on their behalf and do it. But yeah, I think you're not going to be able to catch it from the user's end. And that's probably enough of a reason not to do it online. Yeah, I think voting in person is probably the best you're going to get. Bit of paper, cross it out. I don't know if there's a more secure system than that. It's quite rigorous. The only issue you have is people who do the counting and that. They've got to be checked, and so they're not just got other papers at the ready at the side and swap them in. That's the thing you got to be strict about. Yeah, that's the only downside with it. You know, there's levels to it as well. There's the people who do the counting, then there's, when you take it, you put it on a van somewhere, people in the van, people who take it off the van, you know, and take it to the next facility. Maybe there's levels of counting it goes through, or does it just go to one central place? And, you know, or does someone manage to get a van filled with different votes? They all go in around the, you know, there's all levels to how it could be. You know, if it's not secure, there could be the, yeah, how these things can happen. Or people could just take all the votes and just dump them. Right. There's all sorts of things that can go on. But yeah, I think the in-person is probably the safest thing we got at the moment. But hey, Campaign, how are you doing? Good to see you. I'm just going to get another drink of water, and then we'll launch this shader and see if it blows up my GPU. BRB. Right, welcome back. Doing good, thank you. Good to hear, my friend. Good to hear. Where's my stone rebel, man? Right. So plugging this in. So I think, do I have the Morton codes? And this debugging stuff is good. I want to check it in such that I can always come back to it later, because it's quite good being able to run it, debug it, make sure it's perfect, and then put it up, you know. Put in GPU code, you know. Well, that's pretty cool. So the problem is I don't think I have any more codes on the GPU. So we need, so you get the Morton codes, they come in. You turn them into, you've got to see they're uploaded from the CPU. Is that correct? So most of them are going to get done in the editor, and the editor's going to have a bunch of ellipsoids in 3D space, And then, so because it's in an editor, it needs to live on CPU. And then whenever you change something, you get a list, you rebuild the whole BV. No, you just refit it at some point. You refit it. But when you add something new, you take all the Morton codes, throw them up, and then you do a rebuild. But when you save it, you also do a rebuild because a refit won't be perfect. Yes. So they're always going to come from CPU. So whenever you try and build a BVH, you're going to put it in the upload buffer, and then you're going to read it out of the upload buffer. So maybe we just do put it in upload buffer, and it will go into a memory location, which is, so the Morton codes, what are they? The Morton codes are a thank you. Yes, Rogue One. One of the only good Star Wars films made by Disney. You know? Now witness the firepower of a fully armed and operational battle station. Thank you. Yeah, Disney. I like. I think Mandalorian went bad. The few Book of Boba films, which were the Mandalorian ones, sorry, TV show episodes, which were the Mandalorian ones, weren't bad. Then what else is good from Disney? You've got the Andor. Andor weren't bad. It's quite alright. I watched that a couple of times because I rewatched it with my wife. That was a good one. Yeah, not too many good Disney Star Wars, not gonna lie. Obviously, Star Wars Episode 7 was just pretty basic. Wasn't bad, just basic. Just a setup film. But 8, Episode 8 and 9. The craziest thing was you found out that Emperor Palpatine was back. Ready? On Fortnite. This is how we discovered that Emperor Palpatine came back because he was cloned via Fortnite. And then if you didn't know what Fortnite was because you are a millennial or boomer, you would have gone into the theaters and it would have started with the Emperor's call has been heard across the galaxy. And then you're sitting there thinking, like, when did this happen? I watched Star Wars Episode 8. Was the Emperor in Episode 8? It was just bananas. Like, I can't believe these people have jobs. It's just insane. It is just insane. Rogue One was the only decent Star Wars film I liked since the originals, I think. Yeah, it was one of those things where it didn't necessarily have that super Star Wars feel to it, in my opinion, but it was a really good film that I enjoyed. So, yeah, it was, I enjoyed that. Like, I think when you watch, yeah. Last season of Clone Wars was awesome to see. Yeah, I actually watched Clone Wars very recently. I've since cancelled my Disney Plus subscription because of the recent TV series. But I very recently watched the whole of Clone Wars on there and Rebels. Clone Wars was amazing. And yeah, obviously there's a few episodes which are just filler, but a lot of it was quite good, and you get to see yeah, you get to see more of like how yeah, more of like the clones and sort of their relationship with the Jedi. And there was that episode, and I don't want to spoil it. But yeah. Anyway, I'm not going to try and spoil it. It's good. You should go and watch it. Rogue One, mostly respected, established universe. Yeah, yeah, definitely. It bridged the gap, isn't it? Good times. So are the Morton codes aren't going to live on past. Good goo. So the Morton codes aren't going to live on. So I think we just want a Morton code input output buffer. So you upload to one of them. The Morton code 0 and 1 buffer? Maybe so. So we'll probably have this like as a, hey, this is all the BVH build stuff. Yeah. He eventually went to sleep. I gave him a teddy bear. And he went to sleep. Yeah, so you got the Morton code 0 and 1 buffer. We upload to 0, we write out to 1. So this is the so initially maybe you can call this the uniqueified. And this is the ununiqueified. That'd be terrible. But yeah, this could be like Morton code maybe, or I'm English, I swear. Ununiqueified. Yeah, we gotta keep that in the code base. So I think we'll have our max number of Morton codes. So Morton code max, that just means max number of leaf nodes. Umbra arc. It's hard. Who's Umbra? Known as the shadow world due to the rays of the sun. Sounds familiar. Oh, wait. Yes, we're talking about the same thing. Yes, that thing I didn't want to spoil. I think we're talking about the same thing. Maybe. Yes, that's the exact thing I wanted to talk about. I didn't want to spoil. Yes. That was a good twist. It made me. It was one of the good episodes, I think. Yeah, you can sort of tell something was wrong, and then it validates your what you're thinking. That was good. Amazing. So we want to have a max number of leaf nodes. Meant to do leaves. Proper English, man. Leaves. Yeah, so I want to basically like a leaves capacity. Should I proper English it or not? I don't know. So we're trying. So I don't know how many. 65536 maybe. You just allocate those, and if we get any more, we can always just up that number. So basically, GFX init. We're gonna go ahead and find some room right at the bottom. We're gonna do all the BVH stuff. GPU buffer init. I forget all of this. Debug name, BVH Morton code, ununique. These silly names. Ununiquified. What a name. Then the size in bytes. So we'll just drop that in there. Times by size of E32 for the modern code. And voila. So yeah, so that's for one BVH, the maximum number of leaves, 65k. 64k, sorry. Then you got the uniquifier buffer, same thing. So those get initialized, nice. You then need to actually, so on the first frame, we want to end up creating some somewhere about here. So we want to just build a test BVH. So the first thing I want to do is probably do something like this. BVH. Well, more code uniquifier. I don't really have the E32 on there anymore. Kind of a bit of a waste of space at this point. Yep. So more code uniquifier. Destination buffer is the BVH more code uniquified. Source is the ununiquified. And the number of Morton codes, this always comes from CPU. So we're just gonna put in some value here. So we need to make sure we upload it earlier. So we'll just say like, right. And then we can, so we have to make sure these are zeroed or something like this. If we read the comments, past Henry did us a favor. So these have to be GPU buffers memset. I forget these things. Engine. We've got an engine folder now. Game without engine with an engine folder. Oh, command buffer. Yes, you put the buffer ID, then the word. Neat. The command, the word we're putting in is 0. Set 0. Yep. And then must be sorted. What? Yeah, that's fine. Because it's already... It won't be sorted. So you're going to just have a bunch of nodes, a bunch of ellipsoids, and we'll have to sort them. So that's zeroed. So we've got a GPU sort. It's quite good. So we'll put it in to ununified. There's graphics sort. So there's sort keys. So you just sort them all with a number of entries. And we're just going to say, well, that's based on more code count. Right. Memset. Then looking pretty good. So all we have to do now is actually create some more codes, upload them to here, and then we should be able to test it out, and hopefully that works. Oh, we didn't rename this. BVH Morton. Morton code unifier. How many of these boys and girls we're doing? Well, it's based on this count here. Divide round up 32, like so. And this will be one dimension, one group across the Y and one group across the Z, and voila. So let's go ahead and make that list of Morton codes to try out. We'll put it near all of this stuff because I think, well, we already have a list here, isn't it? Leaf. We can do it again. What I would like to probably do is... Yeah, let's do it near here, but so this is CPU, and we'll do a GPU one. So we're going over, we just have an array of Morton codes. Maybe do 128, and we'll sort the count. In here. So basically, we'll just go over all of those Morton codes. But after, we actually want to position proper ellipsoids. Yeah, so in the next streams, we'll actually be porting over that BVH code anyway. So why don't we just prepare proper ellipsoids, right? In some form of local space. Yeah. I forgot what I settled on. You know, let's just get it working. In the next stream, we'll get, you know, we'll redo this bit because it's only very small, and I need to think about how we're doing our local space thing again. What are we doing with the coordinates? But yeah, we'll just do a round, you know, check a round in there. Off you go. So what do an upload? GPU upload. Upload into buffer, please. The buffer is ununiquified. And we're uploading what exactly? How many bytes? Offset then a size. Offset in bytes and size in bytes. Offset is 0. The size is 128 multiplied, or Morton codes count. Morton codes count multiplied by size of U32. So this gets you back a place to write. So you just mem copy. Well, there we go. So that's going to put them on the GPU at the start of the frame. So they're ready to go. It's going to do a sort. So what's interesting actually is we should be able to read this in RenderDoc and verify it's all correct. Yeah. So hopefully this works. Shoot this. All right, all compiles. Fingers crossed. I think that's right. Let me just double check it quick. So we launched this once at the start based on that. Yeah. Oh, we didn't do the sync code. And we didn't set source here. So read write, read only. We're writing into this one. We're reading from its buddy. And all right, I think that's it. So let's go ahead and hit compile. Now if the stream dies, I'll be right back, but it should be alright, right? Right, stream didn't die, that's a good thing. We run out of what? Nothing. Null ID. Null ID. Right, 844. Null ID. It's a null ID. We didn't initialize the other buffer. Bananas. Thankfully the CPU side saved me. No way. They're both not initialized? What is going on in... Oh, I didn't even assign the ID to the how loony is that? Whoopsie. GPU dot this thing equal that. Wow. Sorry, GFX. Alright, so hopefully this works. If the stream does, I'll be right back. And we're still running. That's a good sign. So what we're going to do is we're going to open up the RenderDoc. The RenderDoc. And we're going to launch the game, do a capture on the first frame, and we're going to see it all in action. So on the GPU now, we have sorted the, to find it. You'll find it here. So there's quite a few for the cube map because we've got PBR with the environment maps and they all get triggered on the first frame. We could have saved them out to disk and just loaded them in, but reasons. There's quite a lot of them, downsampling and all that. Ah, there's a fill buffer here. Interesting. There's a mem set. There's a... That's a sort. Right, there's a bunch of sorting going on here. So should we look at the sort buffer? So view contents. Well, I wanted to do a strut. Well, they're already U32s anyway. What am I doing? Just change that to a... Probably shown as hexadecimal, isn't it? Right, that'll do. So they're obviously not sorted here. No, they are sorted. Sorry, don't mind me. So before the sorting, they're obviously not sorted. I gotta find where that is because it does quite a few passes, you see. Yeah, so before here, yeah, it's not sorted. You can tell this value is bigger than that one. But then when we get to about here, it changed and now it's all sorted from low to high. Got some big old numbers in there. Wait a minute. What is that doing? Oh yeah, it only goes up to one. There's only 128 of them. So these are obviously bogus. Yeah, only goes up to 128. So that's fine. They're all sorted in there. It's good. So then we fill the unique. Sorry, the I'm just confused myself. The unified buffer. We fill that with a bunch of zeros, and then there's a compute pass which runs because there's a barrier. There's a barrier here, so there's another compute pass which runs, which will do the uniquifying. So this could have changed. This will actually store the results in. Let's get the other buffer up. Where's the shader? Uniquified. Or the buffer. Let's try that one. Right. So I want to view this one over here as well. Right, so basically these should be identical except for when there's a duplicate. Now I don't know if we have duplicates. This is where we should probably test that before we upload it, you know. We should probably make it such that it writes two of the same values in and then it figures out how to, you know, we could probably fill it with 0, 1, 2, 3. We could fill it with like we can make it, we know it gets sorted now, so we could fill it with an ordered list, and then just check it, make sure it works. So you basically fill in, maybe what you do is you go divide by 2, we know it's even, right? And we'll just store index divided by 2 plus 0. So this will store 0 to 64. Wait, we're looking at storing duplicates, aren't we? Yeah, 0 to 64. And put them next to each other, sorry. But it should, hopefully. So does it run? The answer is yes. So run in render doc again, and we'll relook at this stuff because it's cool. But yeah, we'll be able to find that nice and easy. So we won't save that capture, and we'll actually have duplicates. We'll be able to analyze and see how they change. So there's the capture. So there's the fill buffer, right? So we know the compute pass is here. So let's take a look at the data. Resource inspector, let's open up this uniqueified buffer and the ununiqueified one. Well, we can't. View contents there, then view contents here. Right, so they're both here. Wait a minute, wrong one. What are you doing? Right, let's double click it. Apply. So obviously, crying out loud. Right, no, this is fine. Why? Yes, the ununiqueified one. Why has it got 4 of them which are the same? Did I accidentally put too many duplicates in? I think I might have, right? Can I read back the code again? So I did. So when index is 0, it'd be then 0, then 1. Then 0, 1. Will be. Yeah. Yeah, okay, I put too many duplicates in, but that's okay. That's okay. So I put 4 duplicates in instead of 2, because I did a divide by 2 here, so that, yeah, I've done it twice. Okay. Anyway, silly me, but that's cool, it still works. So the basic idea is these are the duplicates, right? It just, so it goes up to 32 when it gets to 128, or 31. So we should see our shader, it would have ran over and incremented them such that it's a linear 0, 1, 2, 3, right, all the way up to, right, they should basically always match their index. And if that's true, we just wrote that shader's correct, right? So it's looking good. Just want to double check they're all fine. And there we go. All the way up to 128, so that's good. So now we know that no matter what Morton codes we stick in, they will always, it will take a sorted list of Morton codes and uniqueify them such that we don't have any duplicates. So when we build the tree with the code we've built over the past few days, it will not, that'll be a problem. Right, that's amazing. I think I want to commit that. Yeah, I'll put it up over the weekend for those of you who have access to the source code. But it's been a while since I've last committed. I've not been, yeah, since I restarted, right. So we added basically all the BVH debugging stuff and all the BVH. Yeah. So we began work on BVH. commit-a. So, fully test BVH construction on the CPU and prove on the CPU, ready to be moved to GPU. We also want to say we have also implemented a Morton code unifier. So there will be no duplicate more codes for the BVH tree builder. Right, and I can also just say, we found out that we need to build a binary tree first using more codes, and then construct a quad tree from the binary tree. Right. And then I can drop links. So the binary tree GPU construction comes from these sources. That one, and that one. And then we also then we want to say like the quad tree construction. Yeah, it's just made up basically, isn't it? It was made up on the spot. Obviously, I'll put comments in the code when it comes to that when we port it to GPU. Right, that was super good. Good progress. I want to upload this over the weekend to the repo for those who have access to the repo. If you want access to the repo, there's links in the Discord on how to get that. Basically, if you support via Ko-Fi or Twitch, you can get access to the code. And it runs on Windows or Linux. Yeah, so exciting stuff. We're getting close to actually getting a BVH again. When we have a BVH again, we can just go wild and put a bunch of ellipsoids down and probably move on to taking a break from rendering, because I feel like we've done a lot of rendering episodes. Like if you just take a look at the VODs, we've been doing rendering R&D for like a whole load of time. And thank you, Glorious sir. Yeah, it's good, man. Appreciate you coming by. It's good to see you. And now I know you've seen Star Wars, Clone Wars, so that's cool. Yeah, so since episode 50, we've been doing R&D for rendering spheres and stuff. So it's a long time. It's more than half of this series we've been doing. So I want to get back into doing some other stuff now. As you can tell, right, we did a BVH here, look, before, but we're doing a much better one this time. So yeah, since episode 50, quite literally 51. So what are we on now? 132. So we're doing a lot of rendering, doing like 80 episodes on rendering. So what I would like to do is take a break from that. When we've constructed a BVH, we're going to probably go back into more engine-y stuff. I think what I would like to do is start building some form of editor where we can at least edit a model made out of ellipsoids, right? We're doing ellipsoids now. For those who didn't know, I can't move around for some reason. I think I've disabled my controls. Oh no, I haven't. Here's our ellipsoid, look at it. Boom. Oh. But yeah, when you shrink it to like a flat 2D disk, it will do that glitch. But that's cool, we won't do that much. So yeah, at least get some form of editor in where we can edit a model. So we'll probably take a break from rendering. Think about, because I don't want to just build an editor that edits a model, because it probably takes a lot of code and then it will end up having to be refactored or completely done again. So I think as I'm trying to build this editor, I want to make sure that the code that I'm building will be more sustainable. I don't want to just quickly jam an editor out and make some messy code that I have to just redo again. So I'm thinking we might, while the codebase is not big, make the move to multi-threading. So there is a separation between the main game logic thread and the rendering thread. Maybe we'll do it that way. Maybe we'll investigate something else. And then after that, we can build the editor, right? We'll have a separation of game editor and the renderer. And then with the editor, it will just be built at the moment to edit a model, right? So yeah, I think this is what I'm thinking about more after we've built this BVH. So just taking a nice little break from rendering, getting it so we can build up a nice level, make a few little models, build a nice little environment, and then come back to the rendering and actually work on making the rendering look even better with a scene when we have a scene, right? Yeah, I think that's what we want to do. Thank you, Alex. Good to see you. How you been? But yeah, I think it's gonna be cool. It's gonna be exciting because yeah, we can start building more of a scene after that stuff is done, and the game will feel more gamey, right? There'll be more than just some basic stuff on the screen, at least. Should be cool. But yeah. So when will our next be on? That's a good question. That is Sunday. Wait a minute. It might be a bit late. Yeah, I've got a family due on. But I'll probably be on Sunday. It might be the same sort of time as today. Go back a few hours today, but on Sunday. So 7:30 p.m. GMT +1. Probably about then, maybe a little bit earlier if I'm lucky. But yeah, we'll make a start on. Well, we'll continue on bringing that code over from the CP and building a nice BVH. And yeah, so I'll upload this sometime soon to the repo. Right, and then we'll do a devlog after that. Let's find someone to raid. Oh, let's raid Travis. Right, good to see you all. Have a good start to your weekend. I'll catch you later. Bye bye. Wait, where's the button?